Hello, today we're continuing in our series on nuclear physics, looking at fusion in the stars. When we were considering our fusion reactor, we said that maybe the best thing you could do would be to take hydrogen and just fuse two nuclei of hydrogen together to give you helium. The trouble is that if you keep the numbers constant, 1 plus 1 is 2, 1 plus 1 is 2, you end up with the 2 helium. That would be 2 protons and no neutrons, and that doesn't exist. So we got round that by saying that we would use an isotope of hydrogen, deuterium, which has 1 proton and 1 neutron, and if we fuse 2 isotopes of hydrogen, deuterium, together, we can get 4,2 helium, which is perfectly legitimate, 2 protons and 2 neutrons. And then we went on to say that actually a better solution still was to fuse deuterium with tritium, another isotope of hydrogen, to produce helium and a spare neutron and 17.6 MeV of energy. But then we said that actually that in a reactor, even though we've been doing this for 20, 40 years, goodness knows how long, we still haven't managed to make a reactor that is able to deliver more energy out than it needs to drive it in the first place. But we observe that there is one factory where this is done extremely well and has been done for the past 5 billion years and will be done for the next 5 billion years, and that of course is the sun. So how does the sun manage it? Well, first we need to think about what the raw products are that the sun has available, and for that we need to go back to the time of the Big Bang. Now, exactly what happened at the Big Bang, nobody knows. But the principle is that within a very, very short time, I'm talking less than 10 to the minus 10, less than a 10,000 millionth of a second, 10 billionth of a second, less than that, you've got the formation of all the fundamental particles, the quarks, the electrons, photons. It's far too hot. This is a very, very high energy situation. Far too hot for any atoms to form. So electrons and nuclei cannot come together to form atoms. That won't happen for 380,000 years because it will be too hot. But right in the very early days, you've got the formation of the fundamentals, and the fundamentals come together, the quarks come together to form protons. So you've got essentially the nuclei of hydrogen, and it's hot enough for hydrogen to fuse to become helium, but very little else. And all the time the universe is expanding and cooling. So before you've got any wide-scale fusion of helium to form higher elements, the temperature is too low and any scope for further fusion at that point ceases. So essentially what you've got as a consequence of the Big Bang is a large amount of hydrogen, about 75%, and some helium which has been produced by fusion of hydrogen to helium, and that's about 25%, and very little of anything else, of small bits that will have been fused, but not much. And in fact, that is largely the proportions of elements in the universe today. Nearly all of it still is hydrogen and helium. It shows how little has actually been fused to higher amounts. And I'll show you that a bit later on. But anyway, you've got all this hydrogen and helium splattered around in an ever-expanding universe. And what happens is that gravity starts to take work, and gravity starts to pull all this hydrogen and helium together. So you've got forces that start pulling, and eventually you get down to a smaller amount and gravity continues to pull in. Remember that as these things get smaller, the gravity gets larger because the gravitational force is a 1 over r squared force, so that as the radius decreases, the force increases, so gravity gets stronger, and you're pulling all the hydrogen, mainly hydrogen, some helium, into a ball, and that ball will get hotter, and eventually it will become hot enough for hydrogen to fuse into helium. And when it does, when the fusion takes place, there is an outward pressure caused by the fusion that exactly balances the inward force of the gravity, and so what now has become a star remains stable, because the fusion which is creating all the, as it were, the nuclear explosions inside the sun, producing this outward pressure, balances the inward gravitation. And so you get stability for 10 billion years, actually. But how does the fusion take place? That's the thing that we're most interested in, because what you've got, apart from helium, which is the end product of the fusion that we've looked at so far, the only thing you've got is hydrogen. Critically, you haven't got deuterium and you haven't got tritium. And that's what we were using here. So it looks as though the sun has got to do a hydrogen plus a hydrogen to produce a 2,2 helium, which can't happen. So what's going to happen in the sun that we can't afford to hang around for on the Earth? Because the sun's been going for 5 billion years. And the answer is that the weak interaction operates and takes the nucleus of a hydrogen atom, which is a proton, and converts it to a neutron. And it also spits out a positron and a neutrino. And that's caused by the weak interaction. What is actually happening, let me remind you, is that a proton consists of 2 up quarks and a down quark, and a neutron consists of 1 up quark and 2 down quarks. And what is actually happening in the weak interaction is that that up quark is changed into that down quark, and so a proton has become a neutron, plus these other bits that come out as well. In the sun, the positrons, of course, will not survive for very long. They will just hit one of the electrons in the plasma and annihilate. The neutrons certainly do come out of the sun. Billions and billions of them pass through the Earth. They're passing through you as you watch this video, but you don't notice it, because neutrinos hardly ever interact with any material. So what we've got in the sun is the weak interaction converting some protons to neutrons. And that's a very slow process. And that's essentially why the sun has been going for 5 billion years and has another 5 billion years to go, because if it were a fast process, the sun would have burnt out after a few million years and life would never have formed. So now, instead of saying that we're fusing 2 protons together, which we couldn't do, we're now fusing a proton, which is the hydrogen nucleus, together with a neutron, which is the result of converting a proton to a neutron. And that will give us, of course, deuterium, which is what we're looking for, the isotope of hydrogen, 1 proton and 1 neutron. Then deuterium, which has just been manufactured, can fuse with another proton, the hydrogen nucleus, to produce 3,2 helium. That's helium-3, that's an isotope of helium. And then 2 of those 3 heliums, helium-3, 2 of those can fuse not to produce 6,4, but to produce 4,2 helium plus 2 protons. And both of these 2 processes give off energy. This is about 5.5 MeV of energy given off. This is about 12.9 MeV of energy given off. So you can see that these reactions are the things that are creating the energy that is what is causing the sun to give off energy in the form of heat and light and so on. And that is what is being thrown out as a consequence of nuclear fusion. The sun uses 6 times 10 to the 11th kilograms of hydrogen every second. And that is the equivalent of 4 times 10 to the 38 protons consumed every second. They are either converted into neutrons or they are used to fuse with neutrons to produce the deuterium that is needed to build up to form helium. And that's quite a lot of material. But when you consider that the Sun has a total mass of 2 times 10 to the 30 kilograms, that means that there's enough material there. You simply divide, so you take 2 times 10 to the 30th, which is the total mass, divided by 6 times 10 to the 11, which is the mass consumed per second, and that's going to give you very roughly something like 10 to the 18 seconds worth of material. And I think 10 to the 7 seconds is 1 year, so that is 10 to the 11 years, which is about 100 billion years. In fact, we've got our maths slightly wrong here. That's not going to entirely work. It turns out to be closer to 10 billion years, being the lifetime of the Sun. And part of the reason for that, of course, is that you don't consume all the hydrogen by the time fusion stops in 5 billion years' time. There will still be an awful lot of hydrogen left in the outer layers of the Sun. It's just that the hottest areas in the centre, they will all have been fused into helium. So we don't actually use all the hydrogen, and that's why the lifetime is shorter. And that overwhelmingly is what happens in the Sun. The Sun is just a machine, a factory that converts hydrogen into helium plus energy. And that's the energy that the Sun splatters out. There is in the Sun, and this is very much smaller, a CNO cycle. That's carbon, nitrogen, oxygen. Now, you might say, well, where did the Sun get the carbon, the nitrogen and the oxygen? Well, the answer to that is that the Sun is not, as it were, first generation from the Big Bang. The Sun was formed, 5 billion years ago, but the Big Bang happened 13.7 billion years ago. So there were 8 billion years between the Big Bang and the formation of the Sun. Time for other stars to be born and to die. It's time for the process which I'm going to describe in this video to take place in other stars. Those stars produce huge range of elements. They explode, they splatter their material all round the space. Gravity then causes that to come together, to coalesce, to form another star. And although the overwhelming majority of that star is hydrogen and helium, there will now be bits of elements that were created in previous stars. And carbon can be one of those bits. And so the carbon that is in the Sun, which is, as it were, a relic of a previous star's fusion activities, can now go through this process in our Sun. So you start with carbon 12, 6 protons, and that absorbs another proton. And if you absorb a proton, then you will go to 13, 7 nitrogen. That is proton rich, and if it's proton rich, then you will have beta decay to change a proton to a neutron. So if you get a proton changing to a neutron, then what you will get given off will be a positron and a neutrino, and then one of these protons will be converted into a neutron, and that will mean that you'll have 13,6 carbon being created. That can then absorb another proton. So now if you absorb a proton, you get 14,7 nitrogen created. That can absorb a proton, and that will give you 15,8 oxygen. That now becomes proton rich, and consequently a proton changes to a neutron with the emission of a positron and a neutrino, and that becomes, if you change a proton to a neutron, that will become 15,7 nitrogen. And then what that can do is to absorb a proton, but at the same time to give off a helium, 4,2, and that takes it back to 12,6. If you add a proton, you essentially go to 16,8. If you take a 4,2 off of that, you're back to 12,6. And that's a cycle. You're manufacturing nitrogen and oxygen en route, but once manufactured, it then changes. So you never move away from the fact that you've got some basic carbon 12, You go around this cycle by the absorption of protons, by the emission of these positrons and neutrinos, and indeed a helium nucleus, and you get energy given off. And so that's just a CNO cycle, which is sort of happening incidentally inside the sun. But the key thing about it is that that's a very small part of what is going on, and it doesn't actually manufacture any elements because it just uses the carbon and it goes round in a cycle and brings you back to carbon again. If you look at a chart showing the abundance of all the elements in the universe, it's a logarithmic scale. Along the x-axis we're going to put the Z number, the protons in the element, and then up to here 10 to the 9, and this is 1, and this is a log scale, so every grade is essentially 10 times higher than the one before. I haven't got enough grades, but you get the general idea. Hydrogen and helium are overwhelmingly the most abundant nuclei in the universe. They still hydrogen still has 75%, helium still has about 25%. Everything else is very much less than 1%. If you then look, you go way down here for lithium, beryllium and boron. And then you go up here to carbon, nitrogen, oxygen. And then it sort of wiggles. A little bit of a hike for iron, 56. We'll see why that is a little bit later on, but a bit of a hike there. And then it goes down again and it continues to fall, but in this zigzaggy way, such that the even number, even value of Z is the high point, that's the even, and an odd value of Z is the low point in all of those kind of zigzag things. And we'll see why that is in just a moment. But the whole point is that the abundance of all the elements other than hydrogen and helium is hugely lower than hydrogen and helium itself. So how are they made? Well, hardly at all in the sun as it stands. But what happens at the end of the life of a star? Could be the sun. Here is the sun, and here is the hottest part of the sun, the innermost core. And what is happening in there is hydrogen is fusing into helium. So there comes a point where the core has used up all the hydrogen, and there's plenty of hydrogen, as we said, in the outer layers, but it's not hot enough there for it to fuse. The only place it's hot enough is in the core, and the core is now all helium. All fusion has taken place, but it's not hot enough for helium itself to fuse. Consequently, fusion stops. When fusion stops, the fusion pressure, which was keeping the star stable, because remember, it was the outward pressure of the fusion that was balancing the inner force of gravity and holding this whole thing stable. When fusion stops, there is now outward pressure. Consequently, gravity takes over and the whole thing shrinks. So you've got the hydrogen in the outer parts now coming in and squashing the inner core ever tighter. And if that inner core gets squashed, it gets even hotter. And eventually it can get to a temperature where helium can now fuse. Why do you have to go up to a higher temperature for helium to fuse? Well, it's all about overcoming this Coulomb barrier. Remember that when we were talking about, say, go back to deuterium, when we were fusing two deuterium nuclei together to form 4,2 helium, you've got one proton here and one proton here, so the respective strength of the Coulomb force is going to be 1 times 1, because remember the force, the Coulomb force is Q1 Q2 over 4 pi epsilon naught r squared. So the force is the product of the charge on the two particles. Well, essentially this is one proton, so it's 1 times 1 times the charge on the electron, but forget about that. The relative strength is 1 times 1. When you are fusing two helium nuclei together, you've got 2 protons and 2 protons, so the respective force is 4. This force is 4 times greater than this. So you've got a greater force, greater potential to overcome. Therefore, the nuclei need to be going at a much higher speed. They need to be going at a much higher temperature, so they have a much higher energy to overcome this higher Coulomb potential repulsive force. So that's why you need higher temperatures to overcome the higher Coulomb force. So here, the temperatures are getting hotter, and if they get hot enough, then helium can fuse. So we expect the fusion to take place in the core of this star that is now collapsing due to gravity, and we therefore expect the fusion to be between 2 helium atoms, or 2 helium nuclei. So 4-2 helium plus 4-2 helium. If it's hot enough and can overcome the Coulomb repulsion, then you ought to be able to create 8-4 beryllium, plus some other stuff, and hopefully some energy out. The trouble is that what you find with this is that this actually has a negative Q value. What that means is instead of giving energy out, you have to put energy in to make it happen. Well, that's all right, because the centre of this collapsing star is now very, very hot indeed, so it's got the energy that can cause this to happen. The trouble is that as soon as you've made 8-4 beryllium, actually energetically, it prefers to go back to 2 helium nuclei, because then it will give energy out, and nature is always seeking to find the lowest energy slot. So the minute you make, or the fraction of a second you make this 8-4 beryllium, then 8-4 beryllium will simply decay into 2 lots of helium nuclei, plus energy, and this time it's positive energy coming out because it was negative energy this way. Now you actually get energy given off. This is a lower energy state. So you haven't got anywhere. You fuse the 2 heliums together, you make beryllium, but the beryllium will immediately break up into 2 helium nuclei and give off energy, because nature likes to go to a lowest energy state. And if you can't do that first step, how are you going to ever get anywhere? And this takes place probably in about 10 to the minus 16 seconds. It's almost instant. Well, what you have to assume is that as that 8 beryllium is formed, before it gets a chance to break up, as it would wish to do so, into 2 helium nuclei, it fuses with another helium nucleus to produce 12-6 carbon. Now that's going to be very rare. Most of the time the beryllium is just going to go back to the alpha particles from which it came. But if you are really lucky, just before it can do that, another alpha particle comes along and it fuses and produces 12-6 carbon, but that will be in an excited state. And we've now got another problem. The problem now is that this excited state of carbon has greater energy than 3 alpha particles. So nature, which always wants to find the lowest energy state, will tend to say, very well, I will take my excited state of carbon and I will go to a lower energy state. And that lower energy state is 3 alpha particles. So we're back to where we started. We're back to just having helium nuclei. But very occasionally, the carbon-12 in its excited state can decay to its ground state by the emission of a gamma particle or gamma ray, and we've seen that previously. And that happens 4 in 10,000 occasions. So this process, whereby the carbon just goes back to 3 alpha particles, happens 99.96% of the time. But 0.04% of the time, the excited state of carbon falls to the ground state of carbon by the emission of a gamma ray. And once you've got to the ground state of carbon, put 12.6 there, once you've got to the ground state of carbon, you've got a stable nucleus. Now you've got something on which you can build. So you can see why the sun takes such a long time to get anywhere. First of all, it's got the problem of protons being converted into neutrons by the weak interaction. That takes ages. Then you've got the problem that once you've managed to fuse and produce helium, and at the end of the life of the star, when the fusion of hydrogen to helium stops, the star then starts to collapse, the inner core gets hotter, and it's hot enough now for helium to fuse. Helium fuses into beryllium, but beryllium immediately falls back into the helium. If you're lucky, you can get a beryllium and a helium fusing together to form an excited state of carbon, but most of the time that will just go back to the helium again. We're no further forward. It's just on that very rare occasion where the carbon instead falls to its ground state by the emission of a gamma ray that you get a building block that you can now use to start forming all the other elements. No wonder it takes so long, and no wonder the abundance of these elements is much smaller than hydrogen and helium. But once you've got carbon-12 in its ground state, you've now got the basis of further fusion, and you can take 12,6 carbon and fuse with helium, provided the temperature is hot enough. Remember, every single one of these fusion reactions that I'm going to show you needs higher temperatures. Why? Because you've got 6 protons and 2 protons. The respective Coulomb force is now 12, 6 times 2. And that will give you 16,8 oxygen. And that can fuse if it's hot enough with helium, because now you've got 2 times 8, a respective force of 16. So you need even more energy to get these to fuse together. And that will produce 2010 neon. And then 2010 neon can fuse with another alpha particle if it's even hotter, because now you've got a respective force of 20. Remember when we were fusing hydrogen with hydrogen, the respective force was 1 times 1 is 1. Now we've got 2 times 10 is 20. It's 20 times more difficult. The Coulomb force is 20 times larger to fuse neon and helium than it was to fuse hydrogen and hydrogen. So you can see that the temperatures need to be hugely greater. And that, of course, will now produce 2412 magnesium. And what you can do is you can keep going up in units of 2 protons, because you're adding 2 protons on each occasion. And you can go all the way up to 5628 nickel. And I'll explain in a moment why you can't go any further than that. But let's just observe that what's happening in this fusion process is that the number of protons is increasing by 2 on each occasion. And that explains that chart that I showed you, where we said that the even numbers were much higher than the odd numbers, because this is a sort of a mainstream process, manufacturing succeedingly higher levels of nuclei, which are each 2 protons heavier, as it were, than the one before, until you get to nickel 56. Now, nickel 56 is an unstable nuclei. So, 5628 nickel is proton heavy. So what happens is you get beta decay and a proton converts into a neutron. So that will give you 5627 cobalt. And that is still proton heavy. So that decays by beta emission to 5626 iron. And that is stable. Now, why is there no fusion beyond that? For that, you need to look at the chart that we've drawn many times before. It's the binding energy per nucleon against the A number, the nucleon number. And remember, the shape of that graph is something like this, where the highest value of the binding energy per nucleon is iron 56. So as you fuse the elements together, you're going up this side of the chart, and as you go to higher binding energies per nucleon, remember we showed this before, higher binding energy means you're essentially going deeper into the binding energy, you're going lower. Binding energy is increasing by going lower. That gives off energy. But once you get to iron, if you want to fuse, you're now going downhill. And that means instead of energy being given off, you need to put energy in. So not only do you need the energy that overcomes the Coulomb barrier, which by the time you get to iron 56 is very large indeed, but you also need energy just to make the fusion happen in the first place. And typically the temperatures in the middle of these stars that have come to the end of their natural life and have now collapsed and caused other fusion to take place, the temperatures just aren't hot enough to get beyond this iron 56, as it were, brick wall. So what you end up with is a star where the hottest part of the star, the inner core, has fused, if it's hot enough, all the way to iron 56. And then you'll have rings where the temperatures are progressively smaller and where fusion has therefore stopped because there isn't enough energy to cause further fusion to happen. And typically what you've got is rings of elements which are all 2 protons lighter, all the way out to eventually you'll get helium, and then right on the very end you've got hydrogen. And at that point fusion stops because iron cannot fuse to anything higher, and these have all got to the extent of the fusion for the temperature of the rings. So all fusion now stops. Well, you can guess what happens when fusion stops. Gravity is going to take over again. But before we look at what happens there, we need to address another question. So far we've shown how elements are produced which are 2 protons apart. So all the even number of elements with protons up to iron 56, which is of course 26 protons, they are being made, but what about the odd number? Well, what we've shown is the mainstream cycle where you just keep fusing an alpha particle with the element that's being produced. But that's not the only thing that can happen. For example, 2 carbon nuclei can fuse together. So let's take carbon 12 and fuse it with carbon 12. If there is enough energy, look, you're now talking about 6 times 6, 36 times the force that you would need, that you need to overcome if you were fusing hydrogen with hydrogen. But assuming you've got the temperature to do it, that produces not as you might expect, that's 6 there, not as you might expect 2412 magnesium, but 2311 sodium plus a proton. And that's a reaction that can and does happen, but it's rare for it to happen. It's, or shall we say, rarer for it to happen. Similarly, you can have 2 oxygen nuclei. And if you can fuse those together, look, we've now got 8 times 8, 64 times more energy required than if you were just fusing 2 hydrogens. So clearly you're going to have very hot temperatures indeed for this, but that can produce 3115 phosphorus plus a proton. And so the odd number nuclei are produced by fusion, which instead of producing, as it were, just double this, instead of 3216, it actually produces 3115 and a proton. So that is the mechanism by which the odd Z number, the odd proton number nuclei are produced. But their abundance, of course, is correspondingly lower than the even number. Okay, so we've got to iron 56 in our core. Is there really no way in which we can go any higher than that? Well, there are some mechanisms. For example, we could take 12 carbon and we can fuse that with hydrogen to produce 13,7 nitrogen. And that 13,7 nitrogen, which is now proton rich, will beta decay to 13,6 carbon, plus of course a positron, plus a neutrino. And then we take the 13,6 carbon, which has been produced, and we add or fuse it with an alpha particle, and that produces 16,8 oxygen plus a neutron. All right, there were 17 nucleons, 16 of them go into the oxygen, and the remaining neutron is spare. We have created in this process a neutron, and those neutrons can now be used in the process that I'm about to describe. So let's take iron 56, which as far as we can see is the end point of fusion, and indeed it is, because what we can now talk about is neutron absorption. So this is iron 56, and what we can do is to absorb a neutron, one of those neutrons that we manufactured up here that happens to be flying around. Well, if iron 56 absorbs a neutron, it becomes simply iron 57. Still has 26 protons. That's stable, and it can absorb another neutron to become iron 58. That's stable. That can absorb a neutron to become iron 59. Now, the time scale for all this is long. This is many years. And iron 56 will have to sit around in the core of this star for a long time until a passing neutron created by this mechanism comes along and can be absorbed. Remember, there's no Coulomb problem now because neutrons aren't charged, so there's no Coulomb barrier problem. There's just the problem of waiting for a convenient neutron to pass by in such a way that it can be captured. And that can take many years. So we've built up, we're still at iron, but we're a higher isotope until we get to iron 59. Now that is unstable. So that will beta decay. It has too many neutrons. So neutron will convert to a proton, and that means that you'll go to 59, still the same number of nucleons, but you now go up a proton number 27, and that is cobalt. So we've now produced the next element up, cobalt. And that too can absorb a neutron and become cobalt 60. But that's unstable. So that now has too many neutrons, so it decays by converting a neutron to a proton. And that means we still have 60 nucleons, but we now have 28 protons because we've decayed by beta decay, and that is nickel. So now we've created nickel. And that can absorb a neutron to become 61 nickel. And that can absorb a neutron to become 62 nickel. And that can absorb a neutron to become, can I get it in, 63 nickel. But that's unstable. So that, move this down a bit, that decays by beta decay, where a neutron, it's neutron heavy, neutron rich, the neutron converts to a proton, so you still have 63 nucleons, but you now have 29 protons, and that of course is copper. And that can then absorb a neutron to become 64 copper. And so it goes on. But each one of these processes takes many, many years. So this is very slow. Hence it is called the S, or the slow process. There's also an implication that once you get to iron 59, it's impossible to go to the next. There is no way of going, apparently, to iron 60 because iron 59 will have decayed by beta decay to cobalt in the time that you're hanging around waiting for another neutron to take you up to iron 60. So on the face of it, you couldn't get any elements beyond these brick walls that I'm putting in here, because that element will have decayed before it can absorb another neutron. So on the face of it, any other isotopes beyond this level are ruled out. And yet you find them. So if you find elements that go beyond these brick walls, and if you find elements that are much, much heavier than copper, then there must be another process rather than this laborious neutron absorption process, which relies on the random production of neutrons at a very this is a rare process. Therefore, the whole thing of this is very slow and cumbersome. What you need is an abundance of neutrons. And how are you going to get that? Well, this is where we go back to our star. This is a star that has collapsed from the state of the sun. The sun won't do this because it will never be hot enough. But if you've got a big enough star that gets hot enough, you're going to get this iron core and then the rings of elements which are 2 protons smaller, all the way down to helium and then hydrogen in the outer layers. And then all fusion stops. And as we said, when all fusion stops, gravity takes over again. And so the outer layers of the hydrogen and the helium start to collapse on the intensely hot inner cores. And what happens then? This outer layer hits this very hot inner core and you get the most cataclysmic, gigantic, massive explosion, the biggest the universe can produce. It's called a supernova. There's a kind of a shock reaction. This outer core falls in and then there's an almighty explosion as the whole thing is thrown out. And actually that is called a supernova, and all the bits, mainly hydrogen and helium, that are thrown out into space will in due course be pulled together by gravity to form another star. So the process carries on. But in the centre is subjected to intense pressures from this gravitational collapse. And what happens is that protons and electrons, so positively charged protons and negatively charged electrons, are squeezed together, crushed, to produce neutrons. And that gives you an abundance of neutrons. And indeed, what you will be left with is just a whole set of neutrons. And that's a neutron star. So that's the production of a neutron star. Just the intense pressure takes all these elements, crushes the protons together with the electrons, produces neutrons, and just leaves a huge pile of neutrons. And that's the neutron star. Now a very small neutron star because the gravity has crushed it to a very small size. If that star is sufficiently large, then it goes beyond being a neutron star, and as we've shown when we did the video on black holes, gravity is now so strong that it overcomes all other known forces of resistance. And so the star just gets smaller and smaller and smaller and smaller and smaller and smaller, because there's nothing to stop it until it becomes just a point, and that is called a black hole. But we're not talking about black holes today, we're talking about what is going on. So what is going on is that you've got iron in the core and then other elements outside, and for a brief moment in time you've got an intense pressure which leads to the production of an abundance of neutrons, which means that you can now start with huge temperatures, huge numbers of neutrons. You can now start to think about fusing beyond iron 56. And that is what produces all the elements that are beyond iron 56. As we've seen, the abundance of those in the whole of the universe is very low, but that's where they're produced. And so, as I did with my with the video that I did on how elements are produced, I just closed this video by inviting you to look at any jewellery that you may be having which has got gold in it. Gold ring, gold necklace, gold chain. Look at somebody else's. That gold could only have been produced in one place, in a cataclysmic supernova explosion over 5 billion years ago. And when that gold was formed as the intense pressure of the collapsing star collapsed on the core, producing neutrons and huge temperatures, which meant that elements could be fused even up to gold, with 79 protons, so huge Coulomb forces to overcome. Then the explosion takes place and the gold gets splattered out into space. Then gravity starts pulling all that together so it coalesces into another star, and incidentally into little bits called planets. One of those planets is called planet Earth. And somebody goes out, digs a mine, and finds that bit of gold, takes it, molds it, shapes it, produces the ring or the jewellery or the chain that you are wearing. Just look at that. That was formed over 5 billion years ago in one of nature's greatest cataclysmic explosions. That's pretty remarkable, isn't it?